before we get into inverse functions, I want to make sure we have a clear understanding of what the word inverse means, what the word opposite means. These are all mathematical words. And what the word reciprocal means. Oh, it went yellow. Halloween Town. So, thankfully you can still see it. Oh, it went back. The ghosts are alive.
Wait, are we taking notes?
You can? You need to? Do you believe all those three words are the same? It doesn't really matter. Like whatever's in your, whatever you think it means, it's fine. Whether it really means that or not, you can just say that word when you want to say it. Or do you think mathematically those three words are different in terms of what they explain for you to do? Are they different or are they the same? They are different, right? And do you know that many interchange those words thinking they mean exactly the same thing? Yes? Okay. Inverse is an operation. That reverses another operation. What do you think obvious examples of inverses are? If inverse is an operation. Yeah, like if you add 2, the inverse is 2. Subtract 2. If I multiply times 3, divide by 3. If I square 5, square root, right? And there's actually many examples of what an inverse is. Inverse does not mean opposite. What does the word opposite mean mathematically? Opposite So opposite is a number that is the same distance from 0 on the number line, but on the other side of 0. So, that was a long way of saying this. What's the opposite of positive 6? Yeah, what's the opposite of negative 10? 10. So, if I ask you for the opposite, that now is a number. So, opposite is a number. Inverse is an operation. Play a game? The funny bone? No? Yeah. How about the word reciprocal? Does that mean all the same there? Reciprocal is when the numerator and denominator so when the numerator and denominator are switched, that's the reciprocal. So, what's the reciprocal of 1/2? What's the opposite of 1/2? Yay? And what's the inverse? Well, it doesn't have one because it's not an operation. Oh man, we're there, right? So, today's lesson is on. Now, do you know sometimes you do the reciprocal as an inverse operation? So when you see a fraction that's multiplying, you do the inverse is to do the reciprocal. So they're connected words sometimes. But do you feel like you understand mathematically what we're talking about when we see that vocabulary? So let's come back to our learning packet. This was like a little tangent, another little math word. So when we talk about what an inverse is, we have an understanding. So what is the inverse of a relation? So it's a relation that reverses another relation. So in the relation, and these are going to be functions once we get there, then in these functions, if it says for the function you should add 2 and then subtract 1, the reverse of that would be 2. Add 1 and subtract 2, right? It reverses whatever it says. So we're going to learn that when we have a function, it tells that function to do something. So when you plug in a number, what do? I do this, and then I do this and get my answer, right? What does the inverse do? It takes you back to where you started, right? So we're going to do that a lot in having that conceptual understanding of what inverse is. So notation. There's a symbol for inverse. Did you do this last year with Nasaurus? This is brand new. You're so lucky, right? Get to learn something that you didn't know before. So if R is the relation, the symbol we use, and it's a little confusing because in math, that little -1 could also mean an exponent -1. That means something completely different. So we have a symbol that uses a little -1. The symbol means inverse, but if you saw a number like 2 to the -1, that means the reciprocal. So know if it's a symbol or if it's an exponent. And that is a little confusing because we're using the same number for a symbol and for an exponent. But when you see it, this is not an exponent. That is a symbol. And what does it represent? Inverse. Now what's inverse again? Inverse reverses whatever a function does. A function says, hey, go times 3 and subtract 1. There I am. What does the inverse do? Add 1 and divide by 2, right? Brings you back to where you started. No, did I say 3? No. So, now, we're going to first start understanding it as ordered pairs. Do you see the ordered pairs here? The inverse of that is understanding that x and y have been reversed. So, the x becomes y, and the y becomes x, and that's the inverse. Crazy, right? So, in this example, what would the inverse look like? So these fancy parentheses, instead of 0, -7, it's now -7 and 0. Instead of -1 and 2, 2 and -1. Instead of -4, -2. And then the last one would be 3 and 6. Do you remember the words domain and range? Of course, right? Domain are the input, usually the x's. Range, the y's, usually the output. For the inverse, the domain and the range are reversed. So the domain becomes the range, and the range becomes the domain. And you just have to take a moment to breathe and think before your brain starts doing that, switching around. All right. Next, in order for us to find an inverse function, what's an inverse function again? It's a function that reverses, right? Whatever happened. I have to understand these two concepts because not all functions have inverses. So, only one-to-one functions have inverses. We're going to write down what that means. And a test to see if it's one-to-one is called the horizontal line test. Now, have you ever heard of the vertical line test? Yeah. Yay or nay? So a vertical line test tests to see if it's actually a function. So for instance, if you graph a circle, it fails the vertical line test because a circle is not a function. It's a relation, but not a function. So for this, sometimes when you reverse, you have to be careful that what you come up with is still a function. That both what you started with and what you ended with both are functions. That means that there's an inverse there. Because it can happen when you reverse something that what you end up with is no longer a function and there's not an inverse for it. So, first one-to-one. So a function is a one-to-one if the relation and its function and its inverse are functions. if we map out a function, you would see that for every x, it goes to only one y, and there's no sharing. No other x goes to the same y. 1 to 1. So if you put in a number for x, there's an answer for y, and it's an exclusive relationship. There's no sharing going on. It's just 1 to 1. Now, how can I look off a graph to know if it's a 1 to 1 or not? So, you remember the vertical line test? It's determined to determine if it's a function or not. That means if you draw a vertical line anywhere, it can only hit the graph at one point. The horizontal line test is the same way, but horizontal. No matter where you draw a horizontal line, it can only hit the graph at one point. If you can draw it anywhere on the graph and it hits it at 2 points or more, it fails and there's no inverse. A vertical line test, test 4, is it a function? And what does it mean? No matter where you draw a vertical line, it only hits the graph at 1 point. The horizontal line test sees if an inverse actually exists. Whether if you do the reverse, it stays a function. So the horizontal line test is the same idea. No matter where you draw a horizontal line, you can only hit the graph at 1 point, and then it would be 1 to 1. So the horizontal line test is used to determine whether the inverse of a relation is a function. Both the relation and the inverse both must be functions. So let's start simple. Look at the bottom. Determine whether they are 1 to 1 or not. So how do I use the horizontal line test? No matter where I draw a horizontal line, in number 1, will it only hit that graph at 1 point? Yes or no? So good. That's a 1 to 1. Do you know what we call that function, number 1? A line, right? Let's be simple. Is line 1 to 1? Yes. Does it have an inverse? Yes. Beautiful. 2. No matter where I draw it, would it pass or fail a horizontal line test? Like really fails, right? Like lots of points. This is no. Do you know what we call number 2? Ah, that'll be a mystery for next semester. That's called a cosine function. You say, what? Say what? What? A cosine function. What? There you go. Mystery, right? There needs to be mystery in life. Next semester. Number 3. Hey, what type of function is number 3? Don't disappoint me. What type of function is number 3? There you go. And you could probably say reciprocal, right? Because it looks similar, right? Either one, but you can see it, right? Is it a 1 to 1, no matter where I draw the horizontal line? And the answer is yes. Even though it seems like it's close, where the asymptote is, you still can't draw a horizontal line and hit the graph at more than 1 point. 3 is a 1 to 1. How about 4? What type of function is number 4? Don't disappoint. Huh? Yeah, hey, cube root. Do you have a redo quiz next week on that, right? Square root functions, cube root? Is cube root a 1 to 1? Yeah, no matter where you draw it. 5, what type of function is this? Not a function. Yeah, it's a function. What type of function is this? Where's the axes? Down there. So the upper one here is that not. Horizontal line, right? Is a horizontal line, does it pass or fail the horizontal line test? Fails, right? Every point it fails. Number 6. Do you know that number 6 fails because it's not a function? Is it a function or does it fail the vertical? It has to pass the vertical and the horizontal, and then there's a inverse. This is a sideways parabola. It is not a function. Turn the page. So what's the notation for a function's inverse? So if it's f at x, the notation is -1 with the x. Have you seen that notation and didn't understand it? Or is that brand new? If you have a function and you want to know its inverse, what's the symbol for inverse? That little -1. We know this. Not all functions have inverses. To find the inverse of a function, we replace f at x with y, we interchange x and y, we solve for y, and then we rewrite it. So, number 7, we'll go through this together. In number 7, what type of function is number 7? Oh, you need to know this, right? That is a polynomial. Hey, what's the degree of the polynomial? 1. And a polynomial degree 1 is called a line, right? A line is 1, 2, 1. So how do I find its inverse? So step 1 is, instead of f at x, that means the same as y equals. Now, why do I do that? Because the inverse of that would be x equals 4y subtract 8. Do you see how the x and the y are switched? By switching it, it forces me to undo what's on the right side. How do I get y by itself? I do the inverse of what I see. What's the inverse of subtracting 8? Oh, that would be to add 8. What's the inverse of multiplying times 4? And there it is. And then what's the symbol for inverse? That little negative 1. And it's x plus 8 divided by 4. So I want you to think. If I ask you about this function, whatever number you plug in, what were the operations you do with x? Here I am, I'm x. Now what happens to me? What do you do first? Times what? Are we going to try again? So here I am, I'm x. What do you do first? Multiply times 4, and then what do you do with me? Subtract 8. But I want to go back to where I was. I want to reverse. Beep, 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 beep. So what do I do to go back? Add 8 and then? Add 8 and then? Divide by 4. This reverses whatever this does. So whatever x is, it takes you back to where you started. All right, again, number 8. Do you know what type of function number 8 is? Cube. Not a cube root, but a cube. It's an odd function. Goes up and down forever. That has an inverse. So how do I find its inverse? Do you know that f at x equals y? So we're always going to start this way. X equals, and then 1/2 y cubed subtract 1. So f at x is y. So the x and y are interchanged. Yes? I do that because I need to know how to reverse this to get y by itself. What would you do first? Add 1? Remember that we talked about how do you inverse a fraction? 1/2 times. What do I do? The reciprocal. So what's the reciprocal of 1/2? And then what's the last step to get y by itself? How do I undo this? This was your quiz yesterday, right? How do you undo that? Cube root. And then what's the symbol for inverse again? Is that little negative 1. So it's the cube root of, and I do not need to multiply it out. You can leave it just like that. So I'm going to remind you again. If I am x, and you plug in a number. So let's say you plugged in 2 for x. That's me, x. What would you do first to get an answer? Please excuse my dear Aunt Sally. What would you do first? You'd do the exponent, right? You cube it. So here I am, I'm x. You would cube me. Then what would you do? Whatever the answer is, you go half, and then the last step? Subtract 1. But I want to do the inverse. Beep, 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 beep. How to go back to where I started? You'd add 1, then?
Divide by, multiply by 2.
Multiply by 2, and then the last step? The cube root. So when I plug in a number here, what do you do first? Add 1, and then you? And then lastly, and you're back to where you started. That is what an inverse function does. You with me, Jessica? Awesome. All right, are you ready to help me yet? Number 9. You ready? I want to know if you actually were paying attention. You ready? Number 9. How would you start this problem? How would you start this problem?
Oh, wait.
Yeah, good. Thank you for saying wait. How would you start this problem? Whether you've been listening to me or not, how have I started every problem? No. How have I started every function? What did I ask myself first? Is there an inverse? Right? First question. What does the picture look like? What is it? A quadratic. What does it look like? Yes? Do you think it passes or fails the horizontal line test? Can you picture a parabola in your head? Can you draw a horizontal line, hit it more than one point? Parabola. Draw a horizontal line. Is there anywhere you can draw the horizontal line and hit it more than one point? Yes. Guess what? 9? No inverse. No, there's no inverse. So you know what a parabola looks like. I don't care where it is on the graph. Does it fail? A parabola? So what do we write down? No inverse. On to number 10. All right, Thomas, you ready? What kind of function is number 10? What name do we call it? Yeah, don't disappoint. Starts with an R. What type of function is number 10? We had a big exam on this. Polynomials and? Just say it. No. Your exam was not on polynomials and reciprocals. What was your exam on? That you corrected. On polynomials and?
Radicals.
No, it was not on polynomials and radicals. So, this is called a rational function because we have a quotient, a division, a fraction, and we have a polynomial in the denominator, right? Variables. So what do we call this, Thomas? A rational. Yes? Is a rational one-to-one? And the answer is yes. So, we can find its inverse. We looked at that on page 1, that a rational is a one-to-one. So, Thomas, how do I start this? X equals... Excellent. Now, I'm going to give you support algebraically. The easiest step to do next is to do the reciprocal to both sides. What's the reciprocal of X? Good. What's the reciprocal of the right side? Can you see how now the y, which I'm trying to solve for, is now in the numerator, which makes it easier, right, to get by itself? Thomas, what would you do next to get y by itself? That's what I'm going to do. I am not going to simplify. Whatever operation I do, I just put it there, but I'm not worried about like distributing or doing any of that. So times 5, what would you do next? Done. So that is what's called the inverse. Let's look at number 11. Sarah, what's number 11 called? What type of function is it? And you have great school spirit today. Yes. Number 11. It is a square root function, right? Like what we did last week. Yes? Yes. It is a square root one-to-one. Here's the picture. Is that one-to-one?
Yes.
Correct. Does it have an inverse? Yes.
Yes.
How do I find its inverse?
It is
So x equals negative the square root of y plus subtract 7. What would you do first to get y by itself?
I would add 7.
Excellent. What would you do next to get y by itself?
Divide by negative
What would you do next?
1. And then
Oh,
sorry.
big part.
And you would square it.
I would square this. I'm not going to distribute. And then the last step would be to subtract 2, correct? Now I got something I have to think about. Ask me. I got answers. Me. You good?
Yeah.
You sure? Okay. So, that's the symbol for inverse. Can anyone see what challenge I have right now? Do you see this? If I saw this picture, this is a parabola, right? A parabola has both the top and the bottom, right, when it is. That's not going to match. So what I need to understand, way at the very beginning, what I talked about, inverses means the domain of one becomes the range of the other, and the range of one becomes the domain of the other. I have to know the range so I can write down the domain restriction. Is there a restriction for square root, both domain and range? Then my inverse has a restriction. So is there a restriction here? Is there something it can't be? Then this has it, right? And what I'm looking for is the range, because that will be my domain restriction. So, do you remember how to find domain and range? It comes from h and k. So what's the h? -2. What's the k? All right. Do you know what the negative in front does? Tell me. So it reflects, so this whole picture, right, would reflect down. So do you know what the range would be here? We said the k is -7, yes? So -7 will actually be the top, and then it goes down from there. Meaning the range is going from -infinity to -7. Bottom to top. Thank you. Thomas, it's yours. So, guess what the domain is of my, what's my domain of my inverse? The same as the range of this. So if there's a restriction, we need to know the range to order to write down the domain of the inverse. A little tricky, right? So I can plug in from -infinity to -7, and that's it. This, if I graph it, needs to be half a parabola. All right, number 12. Richard, what's the first thing I ask myself? I ask myself, right, will it pass the horizontal line test? Is it a function that has an inverse?
No.
And so what I picture is the picture.
It's a V shape.
Absolute value looks like a,
V.
it fails, doesn't it? No inverse. Do you know what absolute value, what the picture looks like? Like a V. Does a V fail or pass? Right? Number 13. Can you open that? I'm sorry that someone keeps coming to our door. 13. What type of function is it? And is there an inverse for that function? Thank you. Okay. Everyone gets a sticker like you went to the dentist. So, 13. Do you guys still like stickers? So, those are perfect attendance stickers. So, my children still love stickers, but they're not in high school. So, 13. But maybe you guys still love stickers. Hey, 13. Let's go. Let's see. Cristobal. I want to know my future. So, can you tell me, Cristobal, is a cube root, is that a 1-to-1? Yeah, and you don't have to guess. I'll give you another indicator. Anything with an even exponent is what I'm worried about, right? Or an absolute value. A cube root, the way it looks like a snake, it passes the horizontal and vertical line test. So a cube root is good. A cube is good. A parabola and absolute value, we've got to be careful about. Okay? So number 13, yes. So how do I start this? X equals the cube root of x subtract 9 over 4. What would be the first step? Oh, and that needs to be a y. Cristobal, what's the first step I need to do? We did that. X and y are switched, right? How do I get y by itself? What would I do first to undo? So, the inverse of dividing by 4 is to multiply. What would you do next?
And then get the cube root.
Right? So what's the inverse of cube root? Nope, what's the inverse of cube root? Cube. Yeah, don't make it tough. So the inverse of cube root is cube. And then, last step? That's it. And that's called the inverse. Done. There's no domain restrictions for a cube root, so I don't have to worry about it. It's all real numbers. 14. Alyssa, what's different about number 14? It has a restriction, doesn't it? This is what type of function? Yeah, it's a parabola. And the vertex of this parabola, HK, is 0 and -1. 0 and -1. And it says only graph it when it's bigger than or equal to 0, the x's. So only to the right. And if I look at half a parabola, does that have an inverse? Yes. Now, guess what I need to know? Because I'm going to need it for the inverse domain restriction. What's the range? What's the bottom y value? So we can write it as greater than or equal to -1, or we can say it goes from -1 to infinity. This is going to be my domain restriction when I find the inverse. So how do I set up to find the inverse? I'm going to switch x and y. Instead of y equals, it's now x equals 3y squared, take away 1. Tell me the steps.
We're going to add 1 and this.
Add 1. Done. Next.
And then we're going to divide by 3.
Done. Divide by 3. Next.
And then we're going to square.
Done. No. How do I undo a square?
Or I mean, find it.
No. What's the inverse of squaring?
Find the square root.
That's it. Square root. Do you see as you are telling me? I just took x and just did one thing at a time as you were talking to me. What do you do first? Add 1. Then what? Divide by 3. Then what? Square root, right? And as you're telling me, I'm just writing it down. And that's called the inverse. And again, what's the domain restriction? It goes from -1 to infinity. The range of one becomes the domain of the other. Turn the page. All right, verifying inverses graphically. Two functions are inverses if both functions reflect over the line y equals x. The big word I want you to get is reflect and y equals x. So if you graph a function in its inverse, and you draw the line y equals x, they fold. If you fold it over that line, one would go on top of the other. So what do I get out of this? A function and its inverse. They reflect over which line? Y equals x. Two functions are inverses if both functions reflect over the line y equals x. Two functions are inverses if both functions reflect over the line y equals x. So what we're going to do is we're going to find the inverse, and we're going to graph both lines on this graph. And then we're going to draw the line y equals x and see if it was a reflection or not. All right. So does a line have an inverse? Yes. How do I find the inverse? X equals 3y subtract 6. Davian, what would I do to get y by itself?
Add 6 to both sides.
And then what would you do?
Divide by 3.
You already found the inverse. You see how simple that can be, right? Now, I want to graph this. So to graph it, that 3 belongs to both. So do you see a 1 with the x? That's really 1/3 x plus, and what's 6 divided by 3? And the only reason I'm writing it, because I want to graph it. Isn't that easier to graph mx plus b? So if I want to graph the first line at the very beginning, where would you start to graph it? 1, 2, 3, 4, 5, 6. Would you not go to -6? And then what would you do? Up how many? And to the right how many? Can you take out your ID card and draw your line? So how do you graph a line again? One way is the y-intercept and the slope. There's my line. Now the second line I'm going to do in red for the inverse. How would I graph the second line? Where would I start at? At 2, and then what direction would you go? Up 1 and to the right 3. You don't have to do it in different colors if you don't want to, but I think it's nice to see one and then the other. And then last, I'm going to take green thingamajig here. Do you know how to graph the line y equals x? Like, where would you start at? 0, and then you go up 1 and over 1. In other words, it's like corner to corner, right? If you draw the line corner to corner, that's y equals x. What do you notice about the two lines if you fold it over the green line? If I took this and folded over the green line, what would happen to the red and the black? Do you see that they would go on top of each other? That is a reflection. So a function and its inverse reflects over which line? Y equals x. So if I fold over the green line, one would go on top of the other. We're going to do that again. A function and its inverse, and we're going to graph it. So number 2, what type of function is number 2? Cube. Does it have an inverse? Yes. How do I find the inverse? X and y are switched. Marilyn, what would you do to get y by itself? Subtract 4, and then what would you do? The cube root. That's it. You just found the inverse. I want to graph both of them. Kaylin, do you know how to graph a cube? Like x cubed plus 4? Or do you want support? Are we okay, Kaylin? Can you graph a cube? This is in HK form. What do you think the H and K are? 0 and 4. Can you find 0, 4 for me? Do you know the picture of what a cube looks like? It looks like half a parabola up and half a parabola down. So if I was going to graph this, it'd be helpful to find another point to curve through. So if I plugged in 1 cubed plus 4, what answer would you get? And so I have half my answer. That's part of the cube, right? And then what would be another obvious x value to plug in for the left side? -1. What's -1 cubed? Plus 4 is 3. So can you find -1 and 3? And do you know what the picture looks like in the other direction? Now this one we know, right? Daniela, we know this one. Cube root. That was last week. What's the H and K here? Remember we took the parent points, 0, 0, 1, 1. We're just going to do those three parents, right? 0, 0, 1, 1, -1, -1. And inside, we're going to do the inverse of what it says. Instead of subtracting 4, we're going to add 4. So 0 plus 4, 1 plus 4, and -1 plus 4. And the y values stay the same. So I'm going to find 4, 0. By the way, what do you notice already? 4, 0. What was the first point we started with on the cube? 0, 4, right? They're inverses, right? So 4, 0. 5, 1. And 3, -1. What does this picture look like when it's a cube root? Yes? Doesn't that look fun? So when you do that, if you draw y equals x, which is corner to, can you draw it corner to corner? What do you notice about those two functions if you fold it over the green line? Do you see how one would go on top of the other? So, geometrically, how can you tell if they're inverses? if they reflect over the line y equals x. Hey, how about algebraically? What are we going to do? How can you tell algebraically if two functions are inverses? This takes us to yesterday's lesson. If you take a function and its inverse and compose them, that means that you do a substitution. It will always simplify to x. That's by definition. Remember we talked about a function and its inverse? That whatever a function does, it reverses it and brings you back to x. That's what happens when you do a substitution. So a composite function is a substitution, one inside the other. And if you do that, what would it simplify to if you did the work? X. So I'm going to do that. Are these two inverses or not? So in order to do that, I'm going to do a composite. What happens if you go F composed by G? How do I set that up? So I take G and I substitute it in for X. So it becomes 2x plus 7 minus 7 divided by 2. If they are inverses and you simplify it, all you should be left with is x. So do you see how I took one and plugged it into the other, like yesterday? Now, how about the numerator? What's 7 take away 7? Done. How about 2 divided by 2? Guess what you're left with? They are inverses. So algebraically, what can you do to know if they're inverses? You do a substitution. If you compose a function and its inverse, it always simplifies to x. Let's try that again. Notice how there's a domain restriction. So x squared has an inverse because it's only half the parabola. If there's an inverse, can you substitute in and tell me it's an inverse? So instead of x, what's going in for x? Root x plus 5 squared, subtract 5. Can you take G and plug it in for x and simplify it algebraically? Well, what happens to the square and the square root? They undo each other, right? And then x plus 5 subtract 5, what are you left with? Are they inverses? Let's recap. I'm not sure how much time I got left before the bell rings, but I think I have till 9. So, how can you tell geometrically if they are inverses? Or graphically? If you graph them, they reflect over what line? Y equals x. How can you tell not off a graph if they're inverses? You compose them. Take one inside the other, do the algebra, and it always equals x. Wonderful. Turn the page. So we'll practice until the bell rings. Maybe I'll get to the end of the lesson. The last page is your homework. And if I can't finish, then during my break, I'll continue the lesson on video and send it to you. Deal? Here we go. Number 5. Kim Cruz, you ready? Were you screaming yesterday watching the game? Okay. At least you're honest. So, F composed by G. That's how you know if they're inverses. So, what should I write down if I'm composing?
Okay, so 3 over 2x minus 1 plus 3 and then over 2x.
So do you notice I just take out the x and put in parentheses, and inside the parentheses will be 3 over 2x minus 1 and 3 over 2x minus 1. All right, Kim. Do you know how to add fractions? The denominators need to be the same. So the denominator I don't see under 3 is 1. So what would I have to multiply top and bottom times to make them the same, right? Do you notice the denominator already has 2x minus 1? So 2 times 3 is 6. That's good, right? So if they all have the same denominator, I can multiply times 2x, subtract 1, top and bottom. I only have to look at the numerators. So the first top there is 3. What's 3 times 2? 6x. 3 times negative 1. And then what I'm left with on the bottom is 6. Can you see where we're going now? 3 take away 3 is, and 6 divided by 6, what am I left with? So if you do the algebra correctly, and irrational is the most challenging, then you see it. So, 6, 7, 8, 9. Could you do both? Could you graph it? Could you also do the composite? I'll go to the bell rings with you. So step 1, could you find the inverse? A cube root has an inverse. So find the inverse. Rosie, what would I do first to find the inverse?
You would subtract 2.
Then what?
And then cube it.
That's it, right? Done. So there's my first challenge. Is there an inverse? Yes. And then find it and its function. Can you graph both of them on the graph? Are you okay graphing a cube root? So I'm going to start at 0, 2. I'm going to transform 0, 0, 1, 1, and negative 1, negative 1. So for the cube root, the x's stay the same, and for the y, I'm going to add 2. So 0, 2, 1, 3, and the other one is negative 1 and 1. And for a cube root, do you know what the picture is going to look like? Now, do you see the points we just used? Guess what I can use for the inverse? Instead of 0, 2, I can use 2, 0. Instead of 1, 3, I can use 3, 1. Instead of negative 1, 1, I can go 1 and negative 1. Do you see I took each one, and what's the inverse? 2, 0, 3, 1, 1, negative 1. I just took each point, did the inverse, and plotted them. Now this picture looks different, right? So a cube root compared to a cube. And then if I draw a line, y equals x, which goes through the corners, does it reflect on that line, right? How do I verify algebraically? Is I do the composite. So I take in either order, but I'm going to go g into f. So it's the cube root of, and I take the inverse, which is x subtract 2 cubed plus 2. So I take the inverse and I plug it in to the function. The cube root and the cube undo each other. Negative 2 plus 2, what am I left with? Do you understand that you can graph them at the same time and they reflect over the line y equals x? And when you do substitution, compose one with the other, they simplify to x. All right, number 7. Because there's a domain restriction, the parabola has an inverse. It's only half the parabola, from the x value of the vertex to the right. To find the inverse, we write x equals y plus 4 squared minus 2. Amelia, tell me the steps to undo y.
You're going to subtract, no, add 2.
Then?
You're going to do the square root.
Then?
You're going to subtract.
Perfect. See how when we get good at this, we can just go 1, 2, 3, over. Now, can I graph them? So this is a square root. Do you remember the parent points for square root? 0, 0, 1, 1, and 42. You need to know that next week, right? 001142, square root. Look inside. How is the x changing?
You're adding 2 to
Try again.
it.
Subtracting 2. So to every x, we're going to subtract 2. What's happening to the y's?
You are subtracting 4.
So 0, subtract 4, subtract 4, subtract 4. I'm going to start with inverse. So negative 2, negative 4, negative 1, negative 3, and 2, and negative 2. And then you know what the picture looks like. Here, I'll change colors. I forgot to change colors to the last one. Do you know the other one's a parabola? What can I do with the points I just came up with for the inverse?
You can just switch that.
Everyone, right? So I'm going to go to negative 4, negative 2. I'm going to go to negative 3, negative 1. And I'm going to go to negative 2 and 2. What do you think half a parabola looks like? The picture of it. So there's the vertex. Half of it's going to look like that. I only want half. And then what would happen if I drew the line y equals x? Does it reflect over that line? Would it fold over, and one would be, if I drew it as accurate as possible, right? Can you see how one picture would fold over the other? I think I went over too far, did I? My eyes. 1, 2, yeah, I went over too far. It should have been like here, here, and here. Should have been a little closer to the green. All right. How do I do this algebraically as I do composition? So let's see the setup for that. Nicholas, what would I do to set this up? To do the composition?
You would put
Instead of x, what am I going to put in? Root x plus
root x plus 2
subtract,
subtract 4
and then what's still inside the parentheses?
plus another 4 is squared.
Now, could you simplify what's inside the parentheses? 4, negative 4 plus 4,
0.
and then root x plus 2 squared.
So that would just be x plus 2 subtract 2.
And then 2 take away 2. Does it simplify to x? 8 and 9, we're almost there. Pedro, what type of function is number 8? Yeah, it's a reciprocal. And so I want to find its inverse and graph it. So to find the inverse, I'm going to go x equals 5 over y plus 2. I would subtract 2. You could multiply times y and divide, or you can do the reciprocal. So the reciprocal would make it easier to graph, right? Because then you're going to multiply times 5. And so what you'd end up with the inverse is 5 over x minus 2, right? So what are the 2 points I would transform here? 1, 1, and negative 1, negative 1. So the x is going to stay the same. What's the y going to go? Times 5 and add 2. So 1 and 7. 1, 2, 3, 4, 5, 6, 7. 1 and 7. And negative 1 would be negative 1 and negative 1 times 5 is negative 5. Plus 2 is negative 3. So negative 1 and negative 3. Do you know where the asymptotes would go? It would be h and k. So the h is at 0, but the k is at 2. It's going to look confusing on a graph when you have 2 rationals, but it is what it is. So we have one rational, reciprocal, and the other one that we curved. And then you know what we're going to do with these points we just came up with? We're going to reverse them. So instead of 1, 7, it's now 7, 1. Right?
Yes.
And the other one is negative 3 and negative 1. Where are the asymptotes now? Well, do you remember the asymptote HK? That's been also reversed. So now my horizontal is at 0. And where was the horizontal before? Was at 2. So now my vertical is at 2. So we had x equals 0 and y equals 2. If you reverse it, it's now y equals 0 and x equals 2. There's a lot of stuff happening on that graph, right?
Yes.
I know, right? You're graphing two reciprocals at the same time. It is like a lot of stuff happening, right? And if you draw the line y equals x, they would fold on top of each other. That's the hardest one to graph and its inverse because of that. Now, what would it look like algebraically to prove their inverses? Is you would compose one with the other. So that would mean where there's an x, I would put 5 over x minus 2 plus 2. So I take the inverse and substitute it in. When you're dividing fractions, it's times the reciprocal. When you go times the reciprocal, what do you notice about the 5s? And then negative 2 plus 2, what are you left with? X. We have one more. And then do you have homework to practice? And can you watch this lesson again if you need to? Because I know I'm going quickly, so I can get this in before the bell rings. Here we go, number 9. I can do this. X equals 1/2 the square root of y plus 3. To get y by itself, I'm going to multiply times 2. I'm going to square it, and I'm going to subtract 3. That is the inverse. Times 2, square, subtract 3. I want to graph this. So, to graph it, I'm going to go first to negative 3 and 0. Oh, I failed. I failed. You have the two graphs. You substitute in for the video. Yay, pep rally. And when you simplify, negative 3 plus 3, square root, and square undo each other. 1/2 of 2, we got x. For the video, Mr. G Math.